The second part of this chapter on the stability of state space models is concerned with Lyapunov functions and the so-called Lyapunov's direct method. First, in definition 12.23, we define the concept of a k-function, which is a scalar function that maps from the non-negative reals to the non-negative reals, which has to satisfy three conditions. A, it has to be continuous. B, the function value at 0 has to be equal to 0. And C, it has to be strictly increasing. A k-function is called a k-infinity function if it is, in addition, radially unbounded, meaning that the limit of alpha of r as r goes to infinity has to be equal to infinity. To make sure that we have fully grasped the two concepts of a k-function and a k-infinity function, we look at several examples, and the first one is alpha 1 of x being equal to x squared, which is a k-infinity function because it is clearly continuous. At 0 it's equal to 0, it is strictly increasing, and moreover, if we let x go to infinity, we have that also alpha 1 of x goes to infinity. The second example is alpha 2 of x being equal to the square root of x, which is again a k-infinity function because it is continuous, it is 0 if x is equal to 0, and it is strictly increasing. Moreover, if we let x go to infinity, then also alpha 2 of x will go to infinity. The function alpha 3 of x being equal to 1 satisfies the fact that it maps from the positive reals into the positive reals. However, it's not a k-function and therefore also not a k-infinity function, and that's because it doesn't satisfy that alpha 3 of 0 is equal to 0, and it's also not strictly increasing. The function alpha 4 of x, which is defined as the absolute value of the sine of x times e to the x, satisfies the fact that it maps any positive real number to another positive real number. However, if we sketch this function, we realize that it does satisfy condition A of being continuous and condition B of being 0 for x equal to 0. However, it is not strictly increasing as x increases, even though its upper envelope is the e function, but there are always periods where the function goes back to 0. And therefore, condition C is not satisfied, and hence this is not a k-function, and therefore it's obviously also not a k-infinity function. The final example, alpha 5 of x is equal to the arcus tangent of x, which is a k-function, but not a k-infinity function, as we can see from the sketch provided on the right. It is A, continuous, B, it's 0 for x equal to 0, and it is strictly increasing. However, it converges to pi half as x goes to infinity, and therefore it's not radially unbounded, and hence it's a k-function, but not a k-infinity function. Next, according to definition 12.24, a function v, which now maps from the state space Rn into R, is called a locally positive definite function, or LPDF, if it is continuous and there exists a neighborhood, which we call n, in Rn of the origin, as well as two k-infinity functions, alpha 1 and alpha 2, and a norm such that the locally positive definite function v of x is lower bounded by a k-infinity function of the norm of x, and it's also upper bounded by a k-infinity function alpha 2 of x for all x in the neighborhood n. It is called a positive definite function, or PDF, if it is a locally positive definite function on the neighborhood n, which is equal to the entire state space Rn. Note that an alternative expression for locally positive definite function is Lyapunov function candidate, and a positive definite function is also called a global Lyapunov function candidate. An important class of positive definite functions or global Lyapunov function candidates is provided in proposition 12.25. In fact, for any positive definite matrix P, the function v of x being equal to x transpose px is such a global Lyapunov function candidate. The proof of proposition 12.25 is left as an exercise, and it's a good idea to take a couple of minutes to think about what these two bounding functions alpha 1 and alpha 2 are in this case. This brings us to the theory of Lyapunov functions, which is also called Lyapunov's direct method. And the main idea of Lyapunov's direct method is illustrated on the top of the slide. The basic argument goes as follows. Suppose V is a function that represents the energy of the system. And suppose that we know that the system is passive, so the energy of the system is continuously dissipated. Moreover, assume that the equilibrium point of the system, which is of interest, constitutes a local minimum of the energy of the system. Then, according to Lyapunov's argument, this equilibrium point has to be stable or even asymptotically stable, meaning that the state trajectory eventually has to converge to this equilibrium point. This idea is illustrated in the figure on the right-hand side, where we assume that this two-dimensional function here represents the energy of the system. The energy has a local minimum in the equilibrium point down here, and in blue we see the state trajectory. And since we know that the energy of the state has to go down in every time step, we eventually have to converge to the point of minimum energy. Therefore, what we need, besides v being a positive definite function or locally positive definite function, as shown in this figure here, is a condition on the change of v along the system's trajectory. In particular, we want v to decrease along the system trajectory. In the continuous time case, this puts a condition on the derivative v dot of x of t along the state trajectory x of t of the system 31, which is given by the total differential gradient of v of x transpose times f of x and t. Note that here we have used the chain rule for v of x of t, and f of x and t represents x dot by the state equation 31. What we need, of course, for the energy to decrease along the system trajectory is that v dot of x of t be negative. In the discrete time case, where the state trajectory consists of discrete points in the state space, the change of v is represented by differences in the function v along the discrete states, and by this difference delta v of x of k, we simply mean the difference between v of x of k plus 1 and v of x of k, which we can also express as v of f of x and k minus v of x. And again, what we would want to ensure decrease of the energy is that this difference is always negative. Based on this line of argument, we are now in a position to state a mathematical theorem for Lyapunov's direct method called the Lyapunov theorem. And we first do this for the case of a continuous time system. To this end, we can first define a function v to be a Lyapunov function for the continuous time nonlinear autonomous system if it is a locally positive definite function and it satisfies the decrease condition v dot of x has to be non-positive for all x in the neighborhood, which matches to that of definition 12.24. In other words, being a Lyapunov function is a stronger condition than being a Lyapunov function candidate, which is the same as being a local positive definite function, because a Lyapunov function in addition must satisfy this decrease condition on the same neighborhood where the function is a Lyapunov function candidate. Similarly to before, we call a function a global Lyapunov function if it is a global Lyapunov function candidate, and moreover, it satisfies the decrease condition globally, so for all x in Rn except at 0. Then, theorem 12.27, which we call the continuous time Lyapunov theorem, states the following. A. Suppose there exists a Lyapunov function for the continuous time nonlinear autonomous system. Then the system is stable. If the Lyapunov function is a global Lyapunov function, then the system is globally stable. And B. If, moreover, there exists a k function alpha 3 such that v dot of x is upper bounded by minus alpha 3 of the norm of x, and this decrease condition holds for all x in the neighborhood n, then the system is uniformly asymptotically stable. And again, if everything is global and this neighborhood equals to the entire state space, then the system is globally uniformly asymptotically stable. Analogously, we have in 12.28 the definition of a Lyapunov function for a discrete time nonlinear autonomous system, and that's a function v that maps from the state space into the real numbers, which is a locally positive definite function and satisfies the discrete time decrease condition that v of f of x and k minus v of x has to be non-positive for all x in the neighborhood n except the origin, where n is the neighborhood that was mentioned in definition 12.24 of a locally positive definite function. Again, v is called a global Lyapunov function if it is a positive definite function and it satisfies the decrease condition for all x in the state space except at the origin, so the neighborhood must be equal to Rn. Theorem 12.29 now represents the discrete time Lyapunov theorem, and it states that A. Suppose there exists a Lyapunov function for the discrete time nonlinear autonomous system, then the system is stable. If the Lyapunov function is a global Lyapunov function, then again the system is globally stable. B. If moreover there exists a k function alpha 3 such that the decrease of the Lyapunov function is upper bounded by minus alpha 3 of the norm of x for all x in the neighborhood, then the system is uniformly asymptotically stable. And again, if everything is global, so this neighborhood is equal to the entire state space, then the system is globally uniformly asymptotically stable. The proof of the Lyapunov theorems 12.27 and 12.29 is not extremely hard, but a little bit lengthy and therefore omitted at this point. Moreover, from the energy argument that was supplied before, it is quite obvious why such a result would hold. If, for some reason, you should decide to go deeper into the field of Lyapunov stability, for instance, because you're working with nonlinear systems, then you should be aware of lots of little details, like whether you require alpha 1, alpha 2, alpha 3 to be k functions, k infinity functions, and so on, and whether you need strict inequality or less than or equal to conditions, and these little details. For the purposes of this course, it's sufficient to work with the Lyapunov theorems 12.27 and 12.29. However, as a remark, you should know that there are many similar Lyapunov theorems out there with slightly different assumptions and slightly different statements, and maybe also tailored to a particular class of systems like time invariant systems, periodic systems, and so on. What all of these Lyapunov theorems have in common, though, is that they only provide sufficient conditions for the stability of the system. In other words, if you find a Lyapunov function, then you can deduce some stability property of your system. However, failure to find a Lyapunov function, or even failure for a Lyapunov function to exist, does not imply the instability of the system. Nonetheless, there are also so-called converse Lyapunov theorems, which state that under certain assumptions on the system, a certain type of Lyapunov function has to exist for this system. In the realm of linear systems, which are the subject of this course, the situation is much simpler. The existence of a Lyapunov function is necessary and sufficient, and there exists a constructive way of finding Lyapunov functions via the so-called Lyapunov equation, as we shall see next. For the continuous time case, the Lyapunov equation and its relationship with the stability of a continuous time linear time invariant autonomous system is stated in Theorem 12.30. In fact, if there exists a positive definite matrix P and a positive definite matrix Q that satisfy this continuous time Lyapunov equation, then the system in 37 is globally uniformly exponentially stable. And B, conversely, if the system 37 is asymptotically stable, then for all positive definite matrices Q, there exists a corresponding positive definite matrix P that solves the continuous time Lyapunov equation. We begin with the proof of part A of Theorem 12.30. By proposition 12.25, we know that since P is positive definite, the function v of x, being equal to x transpose px, is a global Lyapunov function candidate. Its derivative v dot of x along the state trajectory is hence given by the time derivative of x transpose px, which by the product rule is equal to x dot transpose px plus x transpose px dot, where we can use the system equation 37 to substitute x dot with a times x, and hence, taking out x transpose to the left and x to the right, we obtain that v dot of x is equal to x transpose times in brackets a transpose p plus pa times x. Since a transpose p plus pa is equal to minus q by the Lyapunov equation 38, we have that v dot of x is less than or equal to minus some k function of the norm of x, and therefore, by the continuous time Lyapunov theorem, we have that the system must be globally uniformly asymptotically stable. By the stability theorem 12.22, for continuous time systems, asymptotic stability of a continuous time linear time invariant autonomous system implies that the real part of all of the eigenvalues has to be strictly negative, and hence the system has to be exponentially stable. And this is a general fact to remember about linear time invariant autonomous systems. If they are asymptotically stable, in the sense that they are stable and the state trajectory converges to the origin asymptotically, then they are exponentially stable. This concludes our proof of Theorem 12.30 part A, whereas the proof of part B is harder and will require several additional steps. Hence, the next 4 slides are dedicated to the proof of Theorem 12.30 part B. The first step is definition 12.31, which defines the Kronecker product of two matrices. So let F be an M by N matrix and G be a P by Q matrix. Then their Kronecker product, written like this, is the MP times NQ matrix given by F11, which is the first entry of the matrix F, times the entire matrix G, F12 times the entire matrix G, and so on in the rows, and in the columns F21 times the matrix G, and so on. So we get a huge matrix which has the dimensions MP times NQ. Next, in definition 12.32, we define the so-called vectorization of a matrix. Let X be an M by N matrix, meaning that it has n column vectors, where each column vector has dimension m. Then the vectorization of X is the mn dimensional vector, which consists of the columns of X stacked up. So we have x1, the first column, then x2, the second column, and so on, down to the last column, xn. Then we formulate proposition 12.33, which states that if A and P are two n by n matrices, their vector products AP, which we define as x, and PA, which we define as y, can also be written as follows. The vectorization of the matrix X, which is the vectorization of the product AP, is equal to the Kronecker product of the n-dimensional identity matrix with the matrix A times the vectorization of the matrix P, and the vectorization of Y, which is the vectorization of PA, is equal to the Kronecker product of a transpose with the n-dimensional identity matrix times the vectorization of the matrix P. For the proof of proposition 12.33, both statements are proved independently. For the first statement, we have to show that the vectorization of AP is equal to the Kronecker product of In with A times the vectorization of P. Now, the Kronecker product of In with A clearly represents a large matrix which carries the matrix A n times on its diagonal. And the vectorization of P is clearly a large vector consisting of the stacked up columns of the matrix P, which we call P1, P2, and so on up to Pn. Thus, this matrix vector product yields a large vector consisting of the single vectors AP1, AP2, and so on down to Apn stacked up on one another. On the other hand, by the basic rule for matrix-matrix multiplication, the matrix product of A times P is equal to another matrix, which consists of the column vectors A times P1, A times P2, and so on up to A times Pn. So, the vectorization of AP is clearly the same vector as we got in the first step. For the second statement, we have to show that the vectorization of PA is equal to the Kronecker product of A transpose with In times the vectorization of P. On the one hand, the Kronecker product of A transpose with In is by definition equal to this big matrix, and the vectorization of P is the stacked up column vectors of P. And therefore, by the basic definition of a matrix vector multiplication, the product of this Kronecker product with the vectorization of P is given by a large vector consisting of stacked up smaller vectors, where the smaller vectors are given by sum over I from 1 to n, ai1 pi, sum over I equals 1 to n, ai2 pi, and so on, down to sum over I equals 1 to n of AIN times PI. On the other hand, by the basic rule for matrix-matrix multiplication, the matrix product PA represents a matrix whose columns are given by these expressions, and therefore the vectorization of PA leads to the same expression as the one that we have obtained here. Next, from proposition 12.33, corollary 12.34 immediately follows, which states that the continuous time Lyapunov equation can be written in vectorized form like this. The proof is really straightforward. By vectorizing the single terms in the Lyapunov equation, we see that the vectorization of A transpose P by this property here is equal to the Kronecker product of IN with A transpose times the vectorization of P. And by this property here, the vectorization of PA is equal to the Kronecker product of A transpose with IN times the vectorization of P. Now we can take out the vectorization of P on the left-hand side, and in the brackets we're left with these two Kronecker products, and on the right-hand side we obviously obtain just minus the vectorization of the matrix Q. Obviously, the Lyapunov equation 38 is equivalent to its vectorization in 39, and therefore it has a unique solution if and only if 39 has a unique solution. The vectorization, however, is nothing but a linear equation system where this expression represents a big matrix, vec P is the unknown vector, and minus vec Q is a known right-hand side vector. Since the matrix of this linear equation system is square, the linear equation system has a unique solution if and only if the matrix is non-singular. And this again is the case if and only if all of its eigenvalues are non-zero. To prove that all of the eigenvalues are non-zero, we have the help of lemma 12.35, where we let lambda 1 through lambda n be the eigenvalues of A. Then first A transpose and A have the same eigenvalues, and B, the n squared eigenvalues of this matrix of our equation system are given by all possible combinations of the sum of eigenvalues lambda I plus lambda j, where I and j have to be selected from the set of integral numbers between 1 and n. Now to the proof of lemma 12.35. The proof of part A is really short, as it follows from the observation that the determinant of lambda I minus A is equal to the determinant of lambda I minus A transpose, which is again equal to the determinant of lambda I minus A transpose. For part B, let Vi and Vj be eigenvectors of A transpose, meaning that A transpose times Vi is lambda I times Vi, and A transpose times Vj is lambda j times Vj. Then we define the scalars u1, u2 up to un as the elements of the eigenvector Vj, and we define the vector w as the stacked up vector of u1 times Vi, u2 times Vi, and so on, down to un times Vi. Now observe that this vector w is an eigenvector of the matrix defined by the Kronecker product of In with A transpose, and that's because the Kronecker product of In with A transpose times the vector w is equal to lambda I times the vector w, which is easily seen by substituting the definition of the Kronecker product, which means that this matrix here is given by the matrix that contains A transpose n times on its diagonal, And if we perform the matrix vector multiplication, we see that A transpose always multiplies the vector Vi, which is equal to lambda I times Vi, and hence we can pull out the scalar lambda I into the front of this vector, and we get lambda I times W. Next, observe that W is also an eigenvector of the matrix defined by the Kronecker product of A transpose with In, because this matrix times W is equal to lambda J times W, as it can be seen by taking a closer look at the matrix that results from the Kronecker product and the vector W, and the mechanics of this matrix vector multiplication. With these two results, it follows that the sum of the two Kronecker products, In with A transpose and A transpose with In (brackets) times W is equal to lambda I plus lambda J times W, and hence any sum of lambda I and lambda J is in the spectrum of this matrix. And since this matrix is an n squared by n squared matrix, and lambda I plus lambda J represents a set of n squared eigenvalues, the claim of lemma 12.35b is proven. By the result of lemma 12.35, the continuous time Lyapunov equation must have a unique solution by the following chain of arguments. First, by the assumption in Theorem 1230b that the system is asymptotically stable, all eigenvalues lambda I of the matrix A have to have a negative real part. So the real part of lambda I is negative for all I from 1 to n. Therefore, also the sum of any combination of eigenvalues, lambda I plus lambda J, must have a negative real part. So the real part of lambda I plus lambda J is negative for all values of I and j in the set of integral numbers from 1 through n. Therefore, according to lemma 12.35, all eigenvalues of this matrix are non-zero. Hence, based on corollary 12.34, the continuous time Lyapunov equation has a unique solution P for every choice of Q. Now, it has been shown that there exists a unique solution P to the continuous time Lyapunov equation if the system is asymptotically stable. For the proof of Theorem 12.30b, it remains to be shown that P is also positive definite. And to this end, we invoke lemma 12.36, where we define the matrix P as the integral from 0 to infinity of e to the A transpose t times Q times e to the AT dt. So we provide an explicit formula for P, and we claim that A, the so defined P, is a positive definite matrix, and B, the so defined P, is the solution to the continuous time Lyapunov equation. Now let's also prove lemma 12.36. For part A, we first use lemma 8.5d, which states that e to the A transpose t is the same as e to the AT transpose. Now, for an arbitrary vector x in Rn, x transpose px can be written as such with the definition of the matrix P. With the definition 10.14 of the square root of a matrix, we can write Q as the square root of Q times the square root of Q. And since x is a time-independent vector, we can pull x transpose into the front of the integral and x into the rear of the integral. So with the fact that the square root of Q is Hermitian and the matrix exponential satisfies this property which we have stated up here, it follows that x transpose px is equal to this big integral, which we can also write as the integral from 0 to infinity of the 2 norm squared of the square root of q times e to the at times x, which is clearly always positive if x is non-zero. And therefore, p is positive definite by definition 10.10. For the proof of part B, we start with the fact that has already been shown that the continuous time Lyapunov equation 38 has a unique solution p bar, meaning a matrix p bar that satisfies that A transpose p bar plus p bar times A is equal to minus q. What we have to show now is that this p bar is given by the formula provided in lemma 12.36. Now let x naught in Rn be any arbitrary initial condition. By Theorem 9.12, the corresponding state trajectory of the continuous time linear autonomous system is given by x of t being equal to e to the at times x naught. Hence, the integral over the derivative of the function x transpose p bar x can be written as x naught transpose p bar x naught minus x at infinity transpose p bar times x infinity, because taking the derivative of this function and then taking the antiderivative cancels out, and hence we have to evaluate this function at the upper limit and subtract the evaluation of this function at the lower limit, which is exactly equal to this if we respect also the minus sign in front of the integral. But now the second term here is equal to 0 because by assumption the system is asymptotically stable, and hence the state converges to the origin as t goes to infinity, meaning that x of infinity is equal to 0. Therefore, minus this integral, which can also be written like this by taking the inner derivative of the expression x transpose p bar x, and which by the product rule yields exactly this matrix in the middle between x transpose and x, and this whole thing is again equal to x naught transpose p bar x naught. By virtue of the Lyapunov equation, we can now substitute minus q for this matrix here, and by the fact that we have expressed the state trajectory up here, we can express x of t by e to the at times x naught. And of course, similarly, x of t transpose is equal to x naught transpose times e to the at transpose. Therefore, by taking the vector x naught out of the integral to the right and x naught transpose to the left, we are left with this equation, which clearly shows that p has to be equal to this integral, and hence we have concluded our proof. Finally, a similar theorem holds for the stability of a discrete time linear time invariant autonomous system of this general form. In this case, we're not going to go through all the details of the proof, but the statements are as follows. A, if there exists a positive definite matrix P and a positive definite matrix Q that satisfy the discrete time Lyapunov equation, which looks like this, so a little bit different from the continuous time Lyapunov equation, then the system is globally uniformly exponentially stable. And B, if the discrete time LTI autonomous system is asymptotically stable, then for any positive definite matrix Q, there exists a positive definite matrix P that solves the discrete time Lyapunov equation.